collaborative localization using dynamic noise, covariance and robot motion model for unknown area exploration. Okay, we see you.
Hello. Can you guys hear me?
Yes.
Yes.
Okay. Hello, everyone. Myself is Dibyendu Ghosh. I'm a research scientist. I'm working for Intel India, Intel Lab, Bangalore. So I'm going to present, just a minute. That's collaborative localization using dynamic noise covariance and robot motion model for unknown area exploration. If you see, like accurate position estimation is one of the major problem in the robotics. Okay, because if you have a very good position estimation, then you will get a very good navigation, and everything will be very control. Also, everything will be very perfect. And when it's coming like in an unknown environment and unstructured environment, and that time the position estimation is more critical and more difficult also. And when it's coming to the multiple robot, and then that time even also, like if you have a wrong localization, then maybe whole robot system will be lost. So here we propose an scheme that where you can without static anchor, how your multi-robot can be localized. So for this, what we did, robots share their own position through the comms communication model, and also they share their relative distance among the robot themselves. That has been measured any kind of sensor. That what we use here basically time of flight sensor, that is called ultra wideband radio. And we also incorporate top of that the dynamic adaptive noise covariance in our sensor fusion model, that is based on extended Kalman filter, and that to improve the localization accuracy. The proposed scheme that what we propose here, that has been tested on the simulated environment, that for this and with the differential vehicle model, and this scheme also we tested right now on our real system. The experimental result that demonstrate like this high level of accuracy in the localization accuracy in the dynamic anchor setup. If you see that basically the traditional way that we do the localization, basically if you put a 3 static anchor, and basically if you do the triangulation, basically trilateration kind of algorithm, and you can easily identify where your robot is. Basically you easily identify where the robot position. And same principle can be used for like in a multiple robot, like in where you have A, B, and C, or all are static anchor, and using a similar kind of method, you easily estimate the position of the robot. But the problem will come when your robot is coming in a lowest kind of scenario where that anchor is not visible, and you can also, if you have a wheel odometry, that after certain time that localization accuracy, localization error will be high, and that time maybe you lost your robot. So based on that, what we are trying to propose here, we are trying to propose to remove this A, B, C, and how the robot they can localize among themselves without 3 static anchor. So main contribution that exploring availability of the properties of the multi-robot system to localize the individual robots, and decoupling the dependency of the static anchor system for our robot localization, and also error modeling and feedback using the dynamic error covariance for improving the localization accuracy. Let's take an main methodology that what we are proposing here. If you did this side, if it is a very conventional way to do the localization, you have a control input, and and on top of that, if you have a wheel odometry or any external sensor, like you can use the visual odometry also. And on top of that, if you put an extended Kalman filter, and you can easily estimate the robot position. But problem is here, as I mentioned, that when the robot will move over time, that error will be accumulated over time. So that's why we top of that, what we incorporate here, that comms part that we are talking about, and at that time robot will share their position, also ranging information, that is D1 and D2 and D3, that with respect to where they are and also distance with among themselves. And also at that certain time that we are taking the timestamp, and the timestamp has been captured, and so with that to just to check when the robot is started communicating. So we can take that time and the control input, so we can easily estimate that how much robot has been moved during that time period. So basically, what if you see, this is the one of the classic. This is the very classical method that we do the robot motion estimation model. If you have a we know the motion model, and robot motion model is, we know that it's a nonlinear model, and so top of that, if we do the Jacobian and that nonlinear motion model, we can do the linearization. And top of that, we can use the Kalman filter, extended Kalman filter, so you can easily estimate the robot state after and delta time. And basically what we'll get, if you give the as a control input at ut at r0, and after delta time, you can easily estimate where will be the r0, and that state will be used for our collaborative localization. Now just take an example that T0, you have you got one measurement, and then in the intermediate point T0 and T1, robot has moved, and that time you don't have any intermediate measurement available for the other robot. So at T0, what I got in the with respect to localize the robot 0, what I got all the distance from the D0 robot 0 to with respect to other. If we have a n number of robots, so I'll get the distance of n vector, and also I'll get the where the robot that time particular time robot was. And also what I got the control input, what that robot is given that particular time. So when I'm getting the next time input, and if I using the previous slide, that motion model, and I can easily estimate that how much robot has been moved after communicating. So using that data, what I'm doing the relative distance, and top of that we have the error, that whatever the movement have been done, that error has been incorporated. Now basically EIJ, basically the state estimated error between that the robots. And for the relative distance displacement DLD, that if we can calculate, that will be the DLD for the if you have n number of robot, it will be a kind of n cross 1 vector. And that whole error vector that has been incorporated dynamically into the Kalman filter. So what if you see that is a sensor measurement, and the covariance of the error that we getting here, that have been incorporated. And we found if we dynamically change the update of the covariance matrix, the error of the localization will be decreased. And using this method, what we did, we generated a simulated environment where we run that robot, like if you see that a robot is moving this kind of structure, and we incorporate the wheel odometry error is almost 1 meter at any time instance, to like similar kind of real time real kind of application to incorporate the huge error into wheel odometry. And top of that, what we did, and if we see that if we increase the robot speed, like in a 0.5, we increase the robot speed like in a 0.5 to 2.3 meter, and we saw if we increase the robot speed, and also if you decrease the communication speed, now if you see the localization error is high. We are getting almost like a 1.5 meter of localization error. That whole area is 20. If a robot is moving in a square of 20 cross 20 meter, and if we increase the FPS of like in a communication speed, like at each 2 FPS, and we see that communication, that localization error is decreased. And if you see, this is a simulated result video that if you see that we simulated this whole setup, like robot number from 4 to 50, and we found that even also if we increase the number of robot after certain time, that localization accuracy remain constant after a certain time. For this particular simulator, if you see, this robot has to be localized with respect to other robots. And if you see at any time, these robots are connected, basically they are measuring the distance from with respect to other. And when this, if you see this green dot is basically the ground truth, and blue dot basically the estimated position. And as I mentioned that we increased the value of the robot, and we found the high accuracy of the robot, high accuracy of the robot localization. And basically now the conclusion, if you see the novel scheme for the collaborative localization, which is maybe this, you can easily remove the static anchor, and that will be like in a scenario, like in a, as I mentioned, like in a disaster kind of scenario, dynamic environment, and unknown area exploration, which will have a lot of impact in future. And that whole system has been set up, has been done in the simulation, and recently we are also doing the same experiment in our real system. And with a simulation, if you see the result, we like scalability aspect, we demonstrate like a number of robot increase number 4 to 50, and we found like accuracy is very high in this particular scheme. Thank you. Questions?
Okay, many thank you. Some questions? So, no questions. Many thank you again. And
thank you for your time. Thank you.
Thank you. And I want to invite the second paper, a control strategy of mobile robots in limited space using a laser rangefinder. Andres Martinez. Okay.
Andres Martinez, we don't hear you.
Oh, yes.
And now?
Yes, yes. Now
Okay, okay. Thank you. So we can start, right?
Yes.
Okay. So the present paper is related to the control, the development of a control strategy of a mobile robot in a limited space using a laser rangefinder. One of the most promising areas of research in the field of robotics is related to the task of creating intelligent autonomous mobile robots able to move in a limited space, bypass stationary or moving by themselves optimal decisions, etc. Nowadays, there are several publications in this field. In most cases, the implementation of algorithms of control for the movement of mobile robots in non-deterministic conditions is associated with a large number of difficulties, such as the complexity of synthesizing the whole information about the environment. Some existing SLAM methods approaches are based on modern and complex computer algorithms. In its implementation depends on the hardware and software capabilities of the platforms on which they are realized. The purpose of this paper is like to present a method for solving the problem of SLAM by the use of a self-developed mobile platform in conditions of limited space. For this task, we have developed an algorithm of control and a visualization software to visualize the construction of the map by the robot in real time. And some experiments have been carried out also. And this algorithm includes some tasks such as the estimation of the current position of the robot, obtained based on the obtained data from the measuring devices in use, the determination of the obstacles and elements of the environment. So in this case, information is saved as time points. And the association of the next task is related to the association of new and previous data. So in this way, we can compare the new data with the previous one, and we can add some new points to the map. And after that, we can update and store the map of the environment. So in here we can see the scheme of control of the robot, the electronics of the robot, and of course also we can see in the second figure the prototype of the mobile robot. So when we have created this prototype, and using this prototype, we have tested our algorithm. So for building the map of the environment, it's necessary to realize some steps like getting the data about the current latitude and longitude of the mobile robot. Using, in this case, we have used a GPS and bonus signal receiver. Then we should get the data about the current position of the robot and coordinates from the LiDAR. We have then it's necessary to build a map using LiDAR and storing the resulting rate of data in memory. So in this case, we can save the information about the current obstacles surrounding the mobile robot. Then it's necessary to do a data filtering process. In this case, we have used a common filter, and then the correction of the map data, it's required. Correction of the map data is required. Then we can assign the current values of the coordinates of the robot and LiDAR. Then we need we have merged the geographical coordinates with the map data array, assigning each point, each map point its own geographical coordinate in accordance with its distance. At the end, we can save the map to a memory card, for example, as it is in our case. So here we can see experimental results we have obtained from the system algorithm we have developed. And here, for example, in figure 3, we can see the visualization of the robot's perception of the environment. And in the next figure, we have the visualization of the map of the environment. The conclusions and future work are the following. We have in this paper present the existing methods for controlling mobile robots in limited space. We have analyzed these methods. We have we present a method for simultaneous localization in mapping, and we have developed a strategy for autonomous control of our prototype. In this case, further, there's going to be integrated as like a camera, just a camera type. Like for example, it can be a Kinect, in order to extend the presented algorithm for 3D reconstruction of an recognition and of static or dynamical targets. Thank you.
Okay. Thank you for your presentation. And now time for questions.
So I have one question. Can I ask?
Okay.
Yes, of course.
So how much accuracy you are getting in your SLAM?
Mm-hmm.
How much accuracy you are achieving?
The accuracy of the SLAM we have here presented, it's about, I think, maybe 80 or 85%.
Okay, so how is that different? That like there is a lot of traditional way to do the SLAM. What is the difference that SLAM and existing SLAM and your SLAM? What was the basic difference?
Mm-hmm. So the main purpose of this algorithm is related like to reduce the resources that we need in terms of the controller, in terms of the control.
So do you have any data related to that? How much is a reduction has been done?
Could you repeat again?
I'm asking that you have any data that how much reduction have been done with respect to existing SLAM algorithm?
No, like
okay.
The information about that, I think no.
Okay, thank
right
you.
Now, no, it's like we are and I think it's a good question, and we should be able, like maybe later, to evaluate the main advantages of that method in taking into account the another existing methods. Yeah.
Okay, thank you.
Mm-hmm. Mm-hmm. You're welcome.